Hello everybody, it's Professor Fiore, and today what I want to talk about is transistor parameters, or really parameters for any device when we make models for devices. This is always good to keep in the back of your head, which is there are parameters that we would like to be constants, but in reality are not constants. In fact, we try to design circuits to sort of be desensitized perhaps to variations in particular parameters. A good example would be the beta of a bipolar junction transistor. But if you take a look at a curve of beta, right here we have typical 3904 transistor. We see a bunch of things going on here. The first and most obvious is that we have three curves of beta. This is a normalized beta out here, HFE, same thing. Off on the vertical, but there's three curves here for three different temperatures, right? Right in the middle is 25 degrees centigrade, warm room temperature, then a rather warm junction temperature of 125 centigrade, and then a nice cool one of 55 below zero centigrade. And we can see that there's variation. The other thing that we see is there's a variation with the collector current itself. So, if we're operating somewhere in the 5 to 10 milliamp range, and we're at room temperature for humans anyway, we get this nominalized or normalized value, nominal value of unity. So whatever we get, for a particular transistor, we can use that as sort of a starting point. If we go to a lower current or a higher current, we see that the beta falls off. If we go to a higher temperature at the same value of current, we get a higher beta. We go to a lower temperature, we get a lower beta. And we still see that variation with current. So we need to remember that this, meaning beta, is not a fixed value. We very often go through computations and we say, oh, beta is 150 or beta is 125 or, whatever it works out to, whatever we're going to use in that problem. And we forget that it is in fact a variable, right? We try to treat it like a constant. We try to design the circuit so that the value of beta is not supremely important and that it's very touchy to the overall response, but we have to remember that there is a variation. And there's actually a third sneaky variation in this diagram. And the question is, can you see it? The clue is up in the right-hand corner. This set of curves is for VCE equals 1 volt. What happens when we change VCE? Now, it's obvious if you're operating a transistor in a very warm or a very cold temperature, right? You might even have sort of an intuitive, reflexive kind of reaction to that. Hey, it's really warm, it's really cold. My beta is going to change, right? You might not have to think about that. You might even remember that there's a variation because of the current. But what about this? Why do they put this in here? Right? VCE is equal to 1 volt. What happens when we change the collector emitter voltage? Well, we can go over to a set of collector curves. So here we have collector emitter voltage on the horizontal and the collector current on the vertical. And each one of these curves, each one of these green lines, represents a certain base current. So at the bottom, right, we have no base current, and we just get a little leakage current, the ICEO, and that continues until we hit breakdown, right? In between the saturation region over here and the breakdown, we have this constant current range where we treat the transistor, we treat this bipolar junction transistor as a fixed current source, right? So here's a certain value of IB, and we get a certain value of IC, right? We increase the value of IB and we get a bigger value of IC. And the ratio of those two, of course, is the beta. But when you look at this, you realize, hey, wait a minute. It's really easy to see on this topmost curve. There is, in fact, a positive slope to this, right? All of these curves come back, if you were to trace them all back. They all meet at a point way out here beyond the edge of the video at a point we call the early voltage, right? So it's easiest to see it on the top one, but there is a variation in current. In other words, if the VCE is some value down here, maybe it's, a volt, 2, 3, something like that, we come up to here, find out the value of IC, divide that IC by this IB, we got our beta. But if we crank up that voltage, right, I'm operating up here somewhere, maybe that's 20 volts, 30 volts. We come up to this line and we now wind up with a slightly higher IC value for that same IB, which means we have a higher beta. And you might recall that's because with the higher voltage, that's a reverse bias on the base collector junction, that increases the depletion region. And it's kind of like you could imagine it's sort of invading deeper into the base region. It sort of effectively narrows the base region. So there's fewer free charges available for recombination, and effectively that makes your beta go up. Some other things that does by expanding that depletion region is it changes the associated capacitance, right? The collector to base capacitance will decrease as we turn up that voltage, as that reverse bias gets larger and larger and larger. Because you could think of that as two plates, right? The collector and the base are like plates of a capacitor, and the depletion region is analogous to the dielectric of a capacitor. So you crank up that reverse bias, it's like separating the plates farther away, capacitance goes down, right? So we tend not to think about that. We tend to think of, beta as being a certain value, okay, maybe for a certain temperature, but do we always have that in the back of our minds that, well, wait a minute, that actually depends on the collector emitter voltage, right? There is going to be a variation. Not a huge variation, it's not going to double or something like that, but there is a variation. And will that impact the overall circuit response? Right? As I said, it would also change things like the capacitance of the device. And this is also true for a JFET, right? Or a MOSFET. You would see similar kinds of things. If you take a look at a set of drain curves instead of collector curves, they look very similar, right? They have the same layout, except this would be for different voltages, right? Different values of VGS, but you would still see this slight positive slope. So there would still be a slight variation in the current, the drain current with the driving gate source voltage. So, all right, what does that mean? That means there's going to be a little bit of a change in the transconductance, which also leads to changes in gain. So we put this all together, right? These are things that hopefully are sort of second order effects and we don't really see them, but how big of an effect can we get, right? We tend not to calculate these things. We have simplified models, right? There's things that we sort of ignore. Remember, a model that we use for a transistor is literally that. It's a model, a tool that we use that reflects reality. It isn't reality. It reflects sort of the major pieces of the reality that we're going to use to simplify our calculations and get results without, going crazy and pulling our hair out. So let's take a look at a little BJT amplifier, right? So what I've done is I've taken this little common emitter amplifier, right? So I've got a signal coming in on the base, simply bypassed over here. I don't even have any swamping. Output on the collector, 15 volt power supply. Now, I've cloned that. I just did a copy paste here on the same circuit. The only real difference is I've changed the power supply. Right, so it's 15 volts over here. On this circuit, you can check through all these resistors are the same size, caps, everything is the same, except this is a 35 volt power supply instead of a 15 volt power supply. And, most of the parameters are not going to change much at all. They're going to change by very, very small amounts. But there are some that will change wholesale. For example, the collector voltage, we're going to see a big change there. When we look down here at the collector, the emitter area, with this bias, most of this 10 volts we know is going to drop across this emitter resistor. And ideally, this base would be 0. In reality, it'll be slightly negative. And then we'll have, of course, the 7/10 or thereabouts across the base emitter. So, maybe we'll get 9.2, 9.3 volts of this dropping across RE. That's going to give us somewhere in the 2 milliamp range, right, with these values. Same exact thing over here. All right, you would analyze these two circuits exactly the same way. Okay, Now with those same currents flowing through the same values of RC, we would expect to see the same exact voltages across those collector resistors. But since this guy is running on 35 instead of 15, this collector voltage is going to be much higher than this collector voltage. And what that means is this collector base junction has a much bigger reverse bias on it than this one does. But virtually everything else is the same between these two circuits. We can go in and do a real quick analysis here on the DC end and just start poking around and looking at points and see what we actually get, right? So like I said, bases should be pretty close to 0. So this one's coming in at negative 81 millivolts. This base is coming in at negative 62 millivolts. This emitter, right? I mean, that's pretty small, right? You got like tens of millivolts. This emitter is coming in at a negative just about 730 millivolts. And this one is about the negative 760 millivolts. So very small changes. If we look at the drops across a given resistor, right, or the current through it, so here's the collector resistor in the first circuit, and that's got 1.95 milliamps through it. If I look at it in the second circuit, it's got 1.96 milliamps, right? So very, very little change here. But when I look at the collector voltages, the DC collector voltage over here is a little over 25 volts, and over here, right, we're only getting a little over 5 volts, which would make perfect sense, right? This is 20 volts bigger than this. And if they have the same drop on RC, then this collector should be 20 volts higher than this collector, okay? But like I said, virtually all the other currents, they're very, 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 very close. But because this does have a much bigger reverse bias, we do in fact expect this thing to have a larger beta. And what does that do? Well, that'll actually increase the Z in base over here. Remember, Z in base is going to be beta times R prime E in a non-swamped amplifier. So even if the R prime E's are virtually the same, you got a bigger beta, that's going to produce, right, a bigger Z in base. What does that do? Well, another thing, of course, is by changing the beta, we'll change the IB value, and that's going to change that little DC voltage that we see here, but not a big change, as we saw. So the Z in base, however, reacts with whatever the generator impedance is, in this case a modest 100 ohms, and that can in fact, particularly if this is large, right, particularly if this is a big resistance, that can impact the amount of front end loss you have on the amplifier. Well, let's go and see what's really happening here. So what we're going to do is, because we have a constant signal input, I'm just going to do an AC analysis, right, of the amplifier itself and see what we get. Since I have the two outputs, VLoad 1 and VLoad 2, we'll do a frequency response plot and see what we get. Well, first thing I'm going to say is these curves are not identical. They're very similar, but they're not identical. So VLoad 2, which the second transistor circuit is the one with the higher voltage, we can see first of all that it has a higher gain. Right? It also appears to go out farther, and we can check this with our little probes here. So the first one, we're getting a gain of about 44.9 dB. All right, I'll put this over here. So about 44.9 dB. This is an unswamped amplifier, so we do expect a pretty big gain. In ordinary form, that's over 100. All right, remember it's a factor of 10 in voltage is 20 decibels, so that's over an ordinary gain of 100, so 44.9. Now let me bring this to 3 decibels down, which would be 41.9. And that'll be the F2 for this, the upper limit frequency. So there's 41.9. So that's coming in at just about 5 megahertz. All right. Now I'll take my second probe and put it on the other circuit. This is the first circuit with the 15 volt power supply. So the gain, right, is a little bit lower. We had 44.9. Now we're getting 44.3 roughly. So we're down, not quite a dB. It's not a huge amount, but there is some loss. But let's also check out the frequency response here, right? So 44.3 roughly would put us down to about 40.3. So 40.3 is right about there. Okay, so on this one, we're getting about 4.3 megahertz instead of about 5 megahertz. So we're definitely a little bit shy in terms of, oh, wait a minute. Did I? Yeah, I went a little too far there. My bad, 44, that's 41.3, not 40.3. 41.3. There we go. Okay, 3.5. That looks a little bit better, right? That spacing should be the same as this spacing. So that's even worse, right? That's 3.5 megahertz for the first one, the green one here on the bottom, and the maroon one, which is the higher bias version, again, about 5 megahertz. So that's a pretty sizable change, in terms of the frequency response. Granted, the gain change isn't that much, but the frequency response change at the top end is sizable, going from 3.5 megahertz to 5 megahertz. All right? Okie doke. Now, same thing is true if we were to look at a JFET. Did the same thing over here. Here's my little self-biased JFET. I cloned it. Same thing, except instead of using a 10-volt power supply, I used a 25-volt power supply. If we go through and look at the DC potentials, everything is going to show up, pretty much consistent, with the exception of, once again, the drain voltages. If I come out on the source, first one's giving us 1.679, and the second one is getting us 1.70. So, virtually the same. Check out the gates. They should be around 0 volts. I'm getting about 44 micro on that one, and 14 micro on that one. So they're tiny, okay? But when I go to the drains, right, this one's giving us just under 20 volts, and this one's giving us just under 5 volts. So again, that change in drain source voltage is going to change some things like the transconductance and the internal capacitances, those lag network capacitances, parasitic capacitances. So let's do the same thing. We'll go in, do a transfer. Hey, same sort of deal we got with the bipolar. This one actually looks worse. Okay, oh, before I forget, here, let me get rid of that. Put down our legend. So VLOAD 2 is the high bias one. That's the maroon one on top. So let's find out what the gain there is. That's sitting at about just shy of 25.5. And then our other one is sitting at about 24.6. So we're looking at about a dB difference, not quite. Again, let's check out what the frequency response is. So if this one on top is 25.47, right, just about 25.5, we're going to be looking at about 22, a little under 22.5 for our breakpoint. That looks pretty good. And on this other one, we're going to go from 24.6 down to about 21.6. Right around there, let's just call that. All right, so the high bias one is sitting at 17.4 megahertz for an upper limit, and the low bias one is sitting at 10.8 megahertz. Now that's even worse than we saw in the bipolar. That's a sizable change. It's not half the bandwidth, but it's pretty darn close to it. I mean, you're probably looking at 2/3 the bandwidth. Okay, that's a pretty big difference. All right, and really, again, the only thing is we just changed the bias. It's 10 volts versus 25 volts. And yet that all creeps in, right? You get a little bit of a change in GM, you get a little change in the capacitance. If you go back and look at the lag network capacitances, I do kind of make a deal about making sure you get a decent value for, your C drain gate or your C gate source or your, same thing on the bipolars, because it will have an impact. And we can see it right here, right? So remember, a model is a model. A model is not reality. A model is an approximation of reality. And we have to keep in mind these models are not perfect. In the real world, there are things that we simplify simply to make our lives a little easier, okay? But it's there, it exists, and let's be honest about it. Many times, not all the time, but many times the variation from device to device, in other words, if I buy 1,000 of these FETs, the variation there will be bigger than the variation I see on, let's say a bias change or a temperature change or something like that. But all those things do exist, and it's worthwhile to keep them in mind when you do these simulations or when you build real circuits. Okay? Great. If you have any comments, any questions, put them down in the comments section. Have a good one. We'll see you next time.